Okay guys, so this is the continuation of chapter 4. Basically chapter 4 is too long. Okay, so you have to be patient to finish it. Now in this video, we will discuss the moment around an axis and not around a point. So far guys, we have discussed the moment around a point of rotation and we have found 4 different methods to find this moment. And don't forget that we said that the moment is a vector, which means it has 3 components in I, j, and k. Now if I need to find the moment around an axis, which means I don't want to find this moment around a point, instead I need to find this moment around any axis that has a unit vector of u. So basically guys, I know that this axis has a unit vector of u and I need to find the moment of rotation around this u. Let's do it. I know basically that the dot product is used in the projection of one vector on any line or on any vector represented by a unit vector. And I know that the cross product is used for the moment. So assume guys that I have this figure right here and I need to find the projection of the moment of this force F around O on any vector u that is basically here y. So I will be more general. I will say that I need to find the moment projection of F around O on any vector that has a unit vector of u. So why should I find the projection? Because basically if I know the moment of a force around O, and this moment is of course a vector, and I need to find the moment around any axis, I can find the projection of the moment around O on this axis. So I will repeat guys, if I know MO in vector form, however I need to find the moment around any axis that has a unit vector u, this means that I need to find the projection MO on this u. So how to find this projection? Let's go step by step. I know basically that M around O is a vector that is equal to R vector cross F. Now what is R? R is the position vector from O to any point on F. And I know that if I need to find the projection of any vector on a unit vector u, I should do the dot product. So here the question is to find the moment around u, which means I need to find the projection of M with respect or of M around O on what? On u. So I need to find the projection of MO around u. And this will be the moment around the unit vector u. So this is equal to what? It is basically equal to the dot product of u and MO. So the dot product is used to find the projection of any vector on a unit vector by doing u dot this vector. So here I need to find the projection of MO on what? On u. So I need to do u dot MO. And this is equal to what? It is equal to u dot the cross product R cross F by doing the substitution of MO. So basically this is what? This is the projection of MO on the unit vector u, which is also what? The moment about the axis u, or the axis that has a unit vector of u. Okay, now the question is, what is m about u that is equal to u dot r plus f? Or how can I find this term or this equation? It is basically called scalar triple product. So it is basically dot cross product. So I'm doing dot of what? Of cross. I know that r cross f could be found using the matrix or using this equation that we have proved in previous video. So this is a cross b or r cross f, or the cross product of any two vectors. And I know that the dot product is xx prime plus yy prime plus zz prime, which is basically the sum of the product of the coordinates of the vectors a and b. So basically, of course, I should start by r cross f. Now, r cross f, using this equation here, so you can find the proof of this equation in previous videos, r cross f is equal to this equation right here, but I will replace ay, of course, by ry, because here I'm doing r cross f, and b by f. Okay, so I will replace basically a by r and b by f. Okay, so basically this is r cross f. I know that in order to find the moment about the axis u that has a unit vector of u, I should find u dot r cross f. So what is u? Basically in vector form. Now what is u? U is the unit vector of any axis. So it is defined as u xi plus u yj plus u zk. So this is u, and my objective is to find u dot r cross f. R cross f is given by this vector here, and u is given by this vector here. So now guys, what I want to do is to do the dot product of u and this vector here. So this is u and this is the vector, and I need to do this dot product. I know that the dot product is a scalar value, it is not a vector. And the answer of the dot product, if I know the coordinates of these two vectors, is xx prime plus yy prime plus zz prime. So if I need to do the dot product of u and r cross f, the answer will be, so u dot r cross f is nothing but x of u times x of the vector r cross f plus y of u times y of the vector r cross f plus z of u times the z of the product r cross f. So basically it is x of u, that is ux, times what? Times x of r cross f, that is equal to ry fz minus fz by, plus y of u, that is uy, times y of f, that is minus rx fz minus rz fx. So of course I should put here minus instead of plus, and finally plus z of u, which is u underscore z, times what? Times Z of R cross F. Okay, so basically this is U dot R cross F. Now let's take a look on the answer of U dot R cross F. First of all, the first question, is U dot R cross F a vector or a scalar? What do you think? It is a scalar because this is the answer of a dot product. So what is U dot R cross F? Basically, U dot R cross F is the projection of the moment around O on U or on an axis that has a unit vector equal to U. Okay, so this is a scalar. It is the projection. I know that the projection is a scalar from chapter 3. So this is a scalar product, and I can find this scalar product using a method that is similar to the matrix method. Let's go to the cross product in matrix form. Okay, so this is the cross product in matrix form, and this was another method to find the cross product. It is basically to put in the first row of this matrix rjk in vector, and then to put the coordinates of vector A and the coordinates of vector V, and then to start by crossing the row of I, the column of I, do this cross product AYBZ minus BYAZ, and then minus J, cross the first row of J, and then, or cross the column of J, the row of J, and then do the cross product of AXBZ minus BXAZ, and then cross K and do the cross product of AXBY minus AYBX. So this was the cross product method. If I need to do the analogy between dot cross or scalar triple product and this cross product, you can see, guys, that if I replace IJK by UX, UY, UZ, I will have the same answer. So basically, guys, this is an analogy. I know that physically it is not relevant. Why? Because I'm replacing vectors IJK by scalars UX, UY, UZ. But this is only an analogy to do that scalar triple product or dot cross product using matrix, because basically matrix is much easier. So if I do a matrix, I don't have to memorize all these terms. So I can do the matrix without memorizing these terms. So basically, guys, I can have the same answer of dot cross product by doing this matrix. So guys, if I want to do this matrix here by putting the coordinates of U in the first row, the coordinates of R in the second row, and the coordinates of F in the third row, and then do the cross product by crossing the column of UAX, crossing the row of UAX, then the answer, the first term will be UAX times what? Times RYFZ minus RZFY. And then minus UAY, and then I do this cross RXFZ minus RZFX, and then plus UAZ times RXFY minus FXRY, which is this term, you will have the same answer. So this result can also be written in the form of determinant or of matrix, making it easier to memorize. Guys, but don't be confused between dot cross and cross. Cross product using the matrix will give me a vector answer, while dot cross using the matrix will give me a scalar answer, which is basically the projection of MO on a unit vector U. Thank you.